Okay, so I wanted to go ahead and just do a quick video on solids. It's not going to be really in-depth, just sort of covering what you need to really know from this section. So when you have solids, they'll organize into, well, some will organize into like this crystalline structure. Crystalline meaning it has like a repeating pattern that it'll basically resemble, right? So what you end up getting from these repeating patterns, you can have the smallest unit, which is results in the cubic unit, or cubic unit cell. That's like the smallest repetition in the pattern. Like if I had like circle, triangle, circle, triangle, circle, triangle, well, my unit would be this first circle, triangle. It's like the first repetition of the pattern. So there's basically three main crystalline structures that you go over. So it'll be simple cubic, body-centered cubic, and then face-centered cubic. So if I were you, literally for the ACS, because they could possibly ask questions on it, is write down this chart that I'm about to like go through. So when I'm talking about something that's simple cubic, consider this shape like this. So this is my ugly cube. I'm not the best, but that's okay. So something that's simple cubic will resemble something like this, where there's going to be at each vertice, there's going to be an atom. And from this, you can determine how many total atoms are in a simple cubic cell. It's not 8, but at each of these vertices, 1/8 of an atom are present. And there are 8 total atoms at the vertices because the square has the 4 up top and then the 4 on the bottom. So it's like 4 vertices or 4 areas it can basically interact. So that means per every simple cubic cell, there's going to be 1 atom. And now this is the important number. So number of atoms. Something else that's like not incredibly important here, it would be the coordination number, which is the number of other atoms one single atom will touch. So that means, like, for example, if I'm looking in reference to this one, it'll touch this one, it'll touch this one, it touches that one, it'll touch one going this way in space, it'll touch one going this way in space, and touch one going that way in space. So it's going to have a coordination number of 6 total atoms. Moving on from that, another important value that you have is the edge length. So the edge length is going to be considered this right here. So the length of the edge. For something that's simple cubic, even though my diagram doesn't really represent it as well, it's going to be 2r, right? Because this is one radius and this is another radius. Pretend I drew them like to scale. If it looks something like that. So 2r is the edge length of something that's simple cubic. And then if you've read the book at all, you'll notice that it says something about packing efficiency. That's not entirely important here, but we'll just keep moving on. So something that's body-centered, kind of fun. So something that's body-centered, the only difference is consider like you had a simple cubic and you just put one atom in the middle here, like in between. So you kind of pushed out these boys a little bit. So if I hope I can draw this kind of okay. So for something that is going to be, well, that's atrocious, but that's okay. I'm getting too fancy. Okay, so for something that is going to be body-centered cubic, there's going to be something in the middle, so like at the body, right? And then there's going to be atoms on the outside again, so it kind of looks like that. Kind of fun, kind of cool. So still again, there's going to be 8 on the outside, so when you want to count up the number of atoms, it's going to be, once again, the 1/8 times 8, and then there's an entire atom in the center, so it's going to be plus 1 atom. So that means per something that's body-centered, it's going to be 2 atoms. And I'm not going to go through it. The coordination number for something that's body-centered is just going to be 8 atoms, meaning it'll touch 8 other atoms. So this edge length is a little wonky. I'm not going into geometry, I'm just going to tell you what it is. So 4r over the cube root 3. And I'll go into like why you need to know these. So moving on to the next one, you have face-centered. So something that's face-centered is going to have an atom at each of the faces, meaning that instead of having an atom in the middle, I'm going to have a big atom at the center of the faces. So something like this. Okay, so I'll have an atom in the center here. I'll have an atom in the center here, 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 and then on that back panel, and then on this front panel. So there's going to be what looks like there's 6, but those, if I'm looking at the simple cubic from this level, the way that it really packs is that half of the atom is outside and half of the atom is inside the simple cubic shape. And then the same thing, there's still just going to be the 4 atoms at the corners. So same thing, it's still going to be the 1/8 plus 8, or the 1/8 times 8. And so because there are 6 faces, and there's half of each of those atoms in there, it's going to be plus 6 times 1/2, so 1 plus 3. So for something that is face-centered, it'll have 4 atoms per cell. And the coordination for something like this is going to be 12 atoms. And this edge length is a little easier, not quite like this one, but it's going to be 2 square root 2 times r. And something you need to keep in consideration here is that this square root 2 does not include the r under it. So that's why I wrote it with parentheses, because your book writes it like 2 square root 2r. And I've seen plenty of students that'll just plug that r under there and get a wrong number. So if I were you, I would memorize this chart entirely, right? So really, the coordination number doesn't really matter as much, but the number of atoms and the edge lengths are what's really going to be important. Because questions you'll end up having will be like, what's the radius of a body-centered cubic cell given a volume of 130 picometers? So BCC with volume is at 130 picometers. So for something like that, you're looking at that and you're like, well, what is this? What am I supposed to do with this? I have volume and I go to radius. So what you need to know is that because these are cubes, right? These are cubes, their volume is equal to length times width times height. But because it's a cube, they all have the same. So it's just going to be your length squared, meaning that if I take the square root of this volume, I will end up with edge length. And so from edge length, I would then want to go to radius. So if I were you, I would do something like 130 picometers. Well, it might actually have it in centimeters. It'd be like, what, 2.32 times 10 to the negative 22nd centimeters, something like that, and it would be cubed because it's volume. So for something like that, I would want to take the cube root of this, so the 2.32 times 10 to the negative 22nd, and I just made up these numbers just off the top of my head, so I'd want to take the cube root to get my length. And so once I have that length, I then want to plug into the equation for edge length of something that's a body-centered cubic, which would be the 4r times the cube root 3. And so from there, I'd multiply over, and then I'd divide by 4. So note, when you do this, though, your answer will be in centimeters, and you'd want to convert them to picometers, or whatever unit the question asks. But usually it'll go into picometers because it's really small. So if I want to go from centimeters to picometers, I would do 1 meter, 100 centimeters, and then times 1 meter, and then 1 meter is equal to 10 to the 12 picometers. So that's the conversion at the very end. So you might want to go ahead and look at conversions again if you're not quite familiar with them. But beyond this, all you really need to pay attention for this chapter is going through the solids, but I don't think I really want to go through those. because it's not entirely important. You could be asked the reverse of this, where it would give you a radius and ask the volume, where you would then just plug in like a radius here and then cube that to get the volume. So just keep into consideration that your volume is just going to be your edge length cubed, because, you know, it's a cube. I've seen questions that ask about density. I don't think for the ACS they would include that, but someone will ask the density of like a face-centered cubic cell that has a volume of, or has a, I don't know, an edge length of blank, or a volume of X, or whatever. And so that's when you have to take into consideration the number of atoms per cell. That's when that becomes important, because you would have to find like so if I want to find density, so if like a question is asking me about density, I need to know whether, you know, it's simple cubic, body-centered, or face-centered cubic, and I want to know how many atoms are in each, and it just goes 1, 2, 4, right? So I need to find the mass of, you know, those 2 atoms or those 4 atoms, depending on what it crystallizes in. So you'd be like, oh, 2 atoms times, I don't know, let's say it's oxygen doesn't crystallize like that. Aluminum has a mass of like 26 point something, but you would want to go, okay, I want to convert to moles, and then I want to convert to mass. It's like 26 point something. And this is where Avogadro's number comes back in. So this is kind of a throwback to Chem 1. But like I said, I don't think this is something that's really going to be tested on. There are really good examples in the book you can follow along with. But really just keep paying attention to this chart. It's really important. I'm telling you, write it, toss it down on whatever scratch paper you have. It will help you to make sure at least you know the number of atoms and then the edge length. Coordination number is not as important, but for sure you definitely need to know number of atoms and edge length. The ACS could ask a couple questions on it, but other than that, I'm having study union. I'm not even going to try and be fancy. Study union, 9 a.m. on Wednesday. So that's December 4th, 2019. So 12/4/19 in the Pegasus Ballroom. If you cannot attend it, it's being recorded through Panopto. And I know several students have been having trouble with Opal. It's not the same software, so don't worry about that. It's recorded with Panopto. So it should be able to be streamed and recorded and held so that you can watch if you can't make it. I know people have class, but just be on the lookout for that. I have a practice exam up on ucfstudyunion.wordpress.com, which I'll be going over, as well as going over some of my notes that I have on electrochemistry and nuclear chemistry, because you guys haven't really touched that. But other than that, feel free to send me questions or just, watch the study unions. There's also other Chem 2 people, so there's several Chem 2 people actually. So there's like 2 SARC tutors and then 2 SI leaders. I recommend you can watch any of these. I would watch as many as you can. So you have up to 8 hours of content from each SI leader for study union. Watch it, take advantage of it. There's tons of worksheets and practice sheets. You guys should all do great.